Hello Chem 1A, this is chapter for lecture video 8, and we're going to be talking about redox reactions, or starting to. Redox reactions are super important to our society, as pretty much every battery, combustion engine, these are a form of redox reactions, or they're at least powered by redox reactions. Redox is shorthand for oxidation reduction reactions. And these are reactions where electrons are being transferred between our reactants. Oxidation is defined as the loss of electrons. So the reactant that loses electrons, we say, would be oxidized. Reduction, on the other hand, is the gain of electrons. So the reactant that gains the electrons, we say, is reduced. I know the word gain and reduction seems funky or silly, but it makes sense if you think about charge. By gaining an electron, because electrons are negative, our charge on that substance is going to be reduced or lowered. One thing that you need to know is you cannot have oxidation without reduction. The electrons that are being lost by the thing that's being oxidized are being gained by the thing that's being reduced. So you can't have one without the other. Now, oxidation reduction reactions are pretty cool. Combustion reactions are a redox reaction, but one of my favorite is thermite. And if you've watched Mythbusters, they actually use the thermite reaction to cut a car in half. The thermite reaction is a reaction that occurs at a very, very, very high temperature. So this is a crucible in this little video down below, and what's going on there is the thermite reaction's going on, and as you can see, it just melted through that crucible. Crucibles are a ceramic cup that is pretty much designed to withstand high temperature. And as you can see, the thermite reaction is just melting straight through it. You can actually do the thermite reaction at home. While I don't actually recommend this, you need aluminum powder and iron 3 oxide, which is rust. So if you can find those two things, then if you just kickstart it with a little bit of a spark or ignition, the reaction will go. And it's very hot and kind of dangerous, so I'd be careful if you try it. Now, before we actually get into really redox reactions in depth, we need to talk about oxidation numbers. Now, what are oxidation numbers? Oxidation numbers are numbers that we can assign to elements within compounds that will allow us to keep track of where electrons are moving from and to in our redox reaction. There are a number of rules for oxidation numbers, and we need to know these. So memorize them, or, as you do more and more of these types of problems, they're going to be kind of more second nature. You're going to get a handle on them. The first rule is that each atom, if it's a pure element in its normal state, right? So O2 gas would be an element in what we call its standard state. It has an oxidation number of 0 in that substance. If we had iron solid, iron is a pure element and it's in its normal state at room temperature, which would be a solid, and therefore its oxidation number would be 0. The second rule is that if we have a monoatomic ion, so instead of iron solid, what if I had iron 2 plus aqueous? Well, the oxidation number is equal to the charge on that individual ion. So if we had Fe2 plus aqueous, then the oxidation number would be 2 plus. If we have Fe3 plus aqueous, then the oxidation number would be 3 plus, because that's the charge on the ion. Now we're going to get a little bit more specific. Certain elements have very specific rules when it comes to oxidation numbers. For instance, fluorine, when combined with another element, so not F2 gas, that would be 0, according to our first rule. But if we had like CaF2, fluorine is in a compound there, and therefore its oxidation number is always -1 when it's in a compound. Or if we had, for instance, OF2, the F's in that compound have oxidation numbers of -1. The oxidation number of oxygen is almost always 2- when it's in a compound. Now, if it's attached to fluorine, which will be pretty rare, or itself, so if we have two oxygens attached to each other, like in peroxide, then with peroxide, the oxygens have a -1 charge, or its oxidation number is -1. When it's attached to fluorine, we actually don't know what it is. We'd have to calculate that or determine it. But almost always, like 99.9% of the time, oxygen, when in a compound, is going to have a -2 oxidation number, and we can pretty much always assume that. Halogens, other than fluorine, chlorine, bromine, iodine, these guys most of the time have -1 oxidation numbers, but there's a lot of instances where they don't, and we'd have to figure out what their oxidation number is. And that's basically primarily when it's attached to an F atom or an oxygen atom. So if we have like ClO3, I have no idea what the chlorine's oxidation number is because it's attached to oxygen in that compound. We'd have to calculate it, and I'll show you how to do that on the next slide. But if it was, PCl3, well, phosphorus isn't fluorine or oxygen. The Cl's in that compound have a -1 oxidation number. The oxidation number of hydrogen is pretty much always +1. This, when it's attached to a metal, yes, it is -1 when attached to a metal. This is exceptionally rare. Negatively charged hydrogen is possible, but super unstable, and therefore not very common. We pretty much can assume hydrogen, when in a compound, is pretty much always going to have this oxidation number of +1. Finally, the last rule here is really how we determine oxidation numbers for elements that aren't on this list. And that basically states that when we add up all the oxidation numbers of all the atoms in a neutral compound, they're going to add up to 0. Or if it's a polyatomic ion, they're going to add up to the sum of the charge on the polyatomic ion. And this will allow us to determine elements that we don't have rules for in terms of their oxidation numbers. For instance, sulfur. We're going to do a couple calculations of oxidation numbers for sulfur on the next slide, using 7 and 1 through 6, the rules that we've just learned here. So let's do that. So let's practice, right? What is the oxidation number on sulfur in the following compounds, right? So we have a bunch of compounds here, and we'll do some more calculations after that. We do not have an oxidation number rule for sulfur, right? So I don't know its oxidation number. But the reason why we don't have an oxidation number rule for sulfur is because its oxidation number actually changes dramatically depending on the compound it's in. Now, this is a neutral compound, and we know that because there's no charge. This means that the oxidation numbers of hydrogen times 2, because there are 2 hydrogens, plus the oxidation number on sulfur, and there's only 1 of that, so we can multiply by 1 if you want, have to add up to 0, right? So I have a rule for the oxidation number of hydrogen. We know that the oxidation number of hydrogen is pretty much always going to be +1. So in other words, I have my oxidation number of sulfur, I'm just going to kind of put sulfur in parentheses here, times 1 plus 1 times 2 has to add up to 0. This gives me 2 plus my oxidation number has to equal 0, or another, my oxidation number of sulfur in this compound is -2. And so here is the answer for the oxidation number in this compound for sulfur. But let's do another example. All right, so let's do SCl2. This again is a neutral compound. So we know that all the oxidation numbers in this compound must add up to 0. So I have my oxidation number of sulfur plus 2 times the oxidation number of Cl. Well, we have a rule for Cl, or all the halogens really.
halogens, unless attached to oxygen or fluorine, are pretty much always going to have an oxidation number of -1. So since I know that, I can erase that and put, hey, 2 times -1, and these guys have to add up to 0 because it's a neutral substance. So I know then that my oxidation number of sulfur is really just going to be plus -2, adds up to 0, or in this case, my oxidation number of sulfur is equal to +2. Notice that in the first compound we calculated, the oxidation number was -2, and now in this compound it's +2. This is a great example of how it can change dramatically. It's not always 2 plus or minus, it could be a different number as well. Let's do some more calculations. So in the case of sodium sulfite, we have two things going on, right? We have two sodium ions, which are H+, and we have one SO3 2-. Now we can include all of this in our calculation here. This is a neutral compound, right? So all of these oxidation numbers are going to have to add up to 0. This is one way to solve it. And so we're going to solve it neutral up here, and we'll solve it polyatomic wise down here. So there's two ways to kind of think about this. We can think of the entire compound as a whole. That's going to be my neutral solution. And in that scenario, I have two sodiums, which have oxidation numbers of +1, plus I have one sulfur, so my oxidation number of sulfur, and there's only one of those, plus 3 times my oxidation number of oxygen. And as we learned in the last slide, oxygen is almost always going to have a -2 overall charge. So I'm going to write -2 here. This all needs to add up to 0. Now, in this scenario, I have 2 plus whatever my oxidation number of sulfur is, plus -6. And that all adds up to 0. This would then solve for, my oxidation number of sulfur plus -4, because the 2 plus and the -6 subtract a little bit here, and therefore my oxidation number of sulfur in this compound is 4 plus. Now that's one way to solve it. That's taking the entire ionic compound as a whole. We included our sodium ions in the calculation. However, I could have just looked at, and I'll do this in a different color, I could have just looked at the sulfite, right? I know that SO3 2-, the sulfur's oxidation number, plus 3 times -2, which is oxygen's oxidation number, has to add up to -2, the charge on my ion. And I could have solved it this way as well. Now what you might notice here is that our sulfur oxidation number, if we solve this out, still ends up being 4 plus, just like we had in the previous solution. So it really doesn't matter which methodology you use when solving for a specific oxidation number within an ionic compound. You can look at the polyatomic in there, or the ion in there, or the whole thing. Whatever you want to do, you feel more comfortable with, do it that way. Okay, so last one, SO4, right? This is a neutral compound again. So we know that the sulfur's oxidation number, whatever it is, plus 4 times -2, this is the oxidation number of my oxygen, has to add up to 0. Or in other words, SOX number, our oxidation number, has to be equal to +8 in this case, if we solve that equation up above. Now, that is my final calculation here. It's very important that when you look at things like this, notice there was no -2 here. This is not sulfate. This is just SO4, which would be sulfur tetraoxide. This is not an ion, so it adds up to 0 and it is neutral. If it was an ion, it would have to have had the charge there in the formula. So this brings us to our last solution. Right now we know our sulfur oxidation number here in this compound is +8. And as you can see, our oxidation number for sulfur can change dramatically depending on the compound it's in, and this is primarily why we don't have a rule for it. Let's do some other calculations here. We have two more. So here's an ion, right? So we know the oxidation numbers of Mn plus 4, because there are 4 oxygens, times -2, oxidation number of oxygen, has to add up to -1, our charge on the ion. Now we're being asked to solve for the metal, which is manganese. So we just rearrange and we solve. If you look here, manganese's oxidation number is equal to +7 in this ion. We can do this here as well. This again is an ion, it's dichromate, and this is a great example because we have chromium, added to 7 times the oxidation number of oxygen, which again is -2. This has to add up to -2 overall. But I missed something, right? There's a 2 here. I need to include that in my formula here for chromium's oxidation number. So when I add this over, what I get is 2Cr is equal to +12, right? Now, this means our oxidation number of chromium in this compound is actually +6. So this is kind of how you have to be able to do this. We're going to need to get good at this because in the next lecture video, you'll see we use oxidation numbers when looking at redox reactions quite frequently. If you have any questions, please let me know. As always, I'm always happy to help.